calculate, and we now see whether these two are equal. Note that. So we start calculating this function. So G composition f is a function from x into z. So we need to calculate its values at these 2 points, 1 and 2. So at 1, what is f of 1? F of 1 is 1, and g of that 1 is also 1. So this is equal to 1. Now G tilde composition f of 1. What about this? F of 1 is 1. G tilde of 1 is also 1. So that means these two are equal. Only one more thing to check. At the point 2. F of 2 is 1. G of that 1 is 1. Write equality afterwards. What about this? F of 2 is 1 and G tilde of 2, G tilde of 1 is 1. You see, although we have 2 here, F of 2 is still 1 and G tilde of 1 is anyway 1. So these two are equal. Hence, we do have these two compositions as equal. Okay, but can we cancel it from both sides to write G equal to G tilde? We cannot, because G and G tilde are not equal. But since you see here we have switched the values, G and G tilde at 2 and 3 they differ. Since G of 2 is not equal to G tilde of 2. And what has gone wrong in this case? F is not surjective, because otherwise we have proved that we can cancel to have G equal to G tilde. Note that F is not surjective. Why is F not surjective? Because the only value of F is 1. F is a function from x into y, right? So only 1 is associated to something in x. 2 and 3 are left alone. So that's why F is not surjective. Thus, the implication this implies G equal to G tilde is not true if F is not surjective. And here the solution ends. Okay. So this was the fourth one. Now we'll look at the fifth one. Let f from x into y and g from y into z be functions. Show that if G composition F is injective, then F must be injective. Is it true that G must also be injective? Is it true that G must also be injective? There is one more part, as you may have guessed. Show that if G composition F is surjective, then G is surjective. And just like that, the previous one. Is it true that F must also be surjective? Okay. So now we look at the solution. What is given to us now? We are given two functions f and g, and you can see that we can form the composition G composition f, because the range of f equals the domain of G. Now if we assume that this composition is injective, then the function, we have to prove that f must be injective. So that's what we assume first. First assume G composition f is injective. We have to show that f is injective. To show that a function is injective, what should we do? We have to prove that if we take distinct points in the domain of the function, then the outputs should be distinct. So, and we have to prove here that f is injective. So for that, we have to take two distinct points in the domain of f. The domain of f is x. So let x1, x2 belonging to x be distinct elements. Now note that G composition f also has x as its domain. So it is given that G composition f is injective. So at these 2 points, the values of this function will also be different, since injective, and we can write it if we want as, although this is understood but still, has x as its domain. We have is not equal to G composition f of x2. Okay. Now we have to, prove that if f is injective, but how do I get rid of G? Now I think if we follow this argument, we won't get anywhere. I have to prove that F is injective. Have I taken it down correctly? F must be injective. Let me see, okay. Or if I come from the other side, if I assume that fx is equal to, okay, so that would be better. Distinct elements. No, not like that. Okay, let me change my strategy a little bit. I have to prove that f is injective. So instead of showing that two distinct elements in X have distinct outputs, I can show that if the outputs are equal, then the inputs must also be equal. Same thing. Okay, so let x1 and x2 be two elements in X such that fx1 is equal to fx2. We could have followed that other argument also, but for some reason it's not coming here. I mean, I'm not able to understand that. So we can use this, we can proceed like this also. We have assumed this. Now we have to prove that x1 is equal to x2. Okay. This implies G composition f x1 is equal to G of f of x1, this is equal to G of f of x2, this is equal to G composition f x2. How does this imply this? It's because you see fx1 and fx2 are two elements in Y, and G is a function with domain Y. So since they are equal, the G outputs should be equal, otherwise G will fail to be a function. So that's why we get this, and by the definition of composition we get this is equal to this and this is equal to this. So what do we have now? We have the fact that the outputs of x1 and x2 under the function G composition f are equal, and it is given that G composition f itself is injective. So that means I must have x1 equal to x2. So since is injective and it has capital X as its domain, let us not just write that, is injective, we have x1 equal to x2. So having assumed that these f values are equal for any two points in the domain of f, we have proved that the points inputs themselves are equal. Hence, f is injective. So that is the first part. Now we have to say, is it also true that G is injective? And this turns out to be not true. I mean, not necessarily true. So next, so we take one example like before. Next, let X and Z be this set and Y be this set 1, 2, 3. f of 1 and g of 1 are defined to be equal to if I define like this, it will look confusing. Let me write it separately. F of 1 is defined to be equal to 1. Okay. F of 2 is defined to be equal to 2. And that's it. That's all for f. G of 1 what is that? The power is gone. So g of 1 is also defined to be equal to 1. G of 2 is defined to be equal to 2. And g of 3, because in the domain of g, which is y, we also have 3, unlike the domain of f, which is x, which has only 2 points. And g of 3 is equal to 1. Okay. It may be somewhat confusing to think of these functions in this way. It's a general advice in mathematics that if you can draw a picture of some situation, then just do it. And for functions, we can always draw pictures. That is the Venn diagram. Let us do that for these functions here. So we have 3 sets, right? This is our x, this is our y, and z is the same as x. Okay, so what does f do? F has x as its domain and y as its range. F of 1 is 1, f of 2 is 2. So this is the function f. What does g do? G of 1 is 1. G of 2 is 2. But g of 3 is again 1. Okay. Now, what about G composition f? See, from this you can see things pretty quickly. G composition f maps 1 into 1 onto 1 because it takes 1 onto 1, and it takes 2 onto 2. So if I write that separately, if I draw it, this is the domain of G composition f, this is the range. It takes 1 onto 1 and 2 onto 2. So you can see that f is injective because it maps different elements onto different elements. G is not injective. It maps both 1 and 3 onto the same element, but G composition f nevertheless is injective. Okay, so even if G composition f is injective, G need not be injective. G may be many to one function also. But f of course is injective. We have already proved that. Without f being injective, we cannot have injective G composition f. So this is the situation. And we can now just see, we write this without using this figure. We have G composition f of 1 is equal to 1. So this is injective, but G is not injective. Since G of 1 is equal to G of 3, although 1 and 3 are different elements in the domain of G. So, if G composition F is injective, then G is not necessarily injective. Okay, so after this, again we have the second part of this exercise. Let's do that in another paragraph. Next, let now our hypothesis is this: G composition F is surjective. We have to prove that G is surjective. That means we have to find, you see this is G, right? For any element here, we have to find an element Y in Y such that G of Y is equal to Z by the definition of surjectivity. That's what we have to show. So we start by assuming, taking any element in the range of G. Let belonging to Z be. Do I have to prove that G is surjective? What does the exercise say? Yeah, G must be surjective. So that means I have taken Z in Z, okay. B, any element. Okay, now what is the domain of G composition F? X, and what is the range? Range is Z. So you see, since G composition F is surjective and this is any element in the range of this function, so there will be one input for which this is an output. That means we can write like this: since this is surjective, there exists an element X belonging to X such that G composition F of X is equal to Z. Okay. Note that Fx is an element in Y. Why? Because X is an element in X and F maps X into Y. So Fx will be an element in Y. For which G of Fx is equal to G composition Fx is equal to Z. From here we are getting this. So what have we got here? We have obtained an element in Y, which is the domain of G, and that element is mapped onto Z by G, and that's what we were seeking. We were trying to find an input for which Z is the output. Under what function? Under G. So that's why, hence, G is surjective. Okay, now what happens to F? Is F also surjective? Not necessarily. And this same example works. The above example also shows that if G composition F is surjective, then F is not necessarily surjective. One can look at the example and see why, but here the solution ends. But let us quickly see, since we already drew the figure, so we can look at that once more, just to see what we are saying is actually the case. So this is F, this is G, and this is G composition F. Okay. You see, G composition F of course is surjective because every element in its range is coming from something. G is also surjective because every element in the range of G is coming from something in the domain of G. But F is not surjective because this element 3 in the range of F is not coming from anything in the domain of F. So the same example works for both the cases. So that ends the fifth one. Okay, now we look at the sixth exercise. Let F from X into Y be a bijective function and let this be its inverse. Okay, we have already seen what the inverse of a bijective function is. Verify the cancellation laws. Okay, what cancellation laws? F inverse Fx is equal to x for all x in the domain x of F, and F of F inverse of y is equal to y for all y in the domain y of F inverse. Conclude that F inverse is also invertible and has f as its inverse, that is this. Okay, so in this exercise we are given a bijective function and we are also given its inverse. Then for these two functions we have to prove this sort of cancellation clause, that if we apply f on some point in x and on that output we again apply f inverse, because that output will be in y, so on that we can apply f inverse, we will get that input back. And a similar thing with f and f inverse switched, their positions switched, and from these two things we have to conclude that the function f inverse itself is also invertible and its inverse is nothing but f. Okay, so let us now see its solution.